Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. There is something fitting about exploring black holes in the quiet hours before sleep. They are, in the most literal sense, the darkest objects in the universe, regions where even light cannot escape, where space-time curves so sharply that all paths lead inward, where the physics that describes the rest of reality reaches its limits and falls silent. They are invisible by definition, known only by their effects, detected only by the disturbances they create in the fabric of space around them. And yet they are among the most studied, most theorized, and most philosophically provocative objects in all of science. Tonight we move through everything science currently knows about them, and perhaps more importantly, through everything it does not yet know. The facts themselves are remarkable enough, but it is the open questions, the genuine unsolved mysteries that sit at the edges of what black hole physics has established that make this subject one of the most intellectually alive areas in all of contemporary science. The established facts here are real. The mysteries are genuine. And all of it, in its way, is very large and very dark and very far away. The ideal material for the hours when the mind is ready to let go of smaller things. A black hole is a region of space-time in which the gravitational field is so strong that nothing, not matter, not radiation, not light itself, can escape once it has crossed the boundary called the event horizon. This is not a theoretical abstraction or a metaphor. It is a precise physical description of a region of space with specific, measurable properties. The event horizon is not a physical surface. There is no wall, no membrane, no barrier you could touch. It is a mathematical boundary, a threshold of no return, defined entirely by the geometry of space-time in that region. From outside, nothing distinguishes the event horizon from any other point in space. From inside, all paths through space-time, every possible future trajectory of any particle or photon, converge toward the singularity at the center. Once inside the event horizon, escape is not merely difficult. It is geometrically impossible in the same way that traveling backward in time is geometrically impossible. The concept of an object from which light cannot escape was first considered, remarkably, in the 18th century, long before Einstein's general theory of relativity provided the theoretical framework for understanding why. In 1783, the Reverend John Michell, an English natural philosopher and clergyman, published a paper in the Philosophical Transactions of the Royal Society in which he applied Newtonian mechanics to calculate the radius a star would need to have at a given mass for the escape velocity from its surface to equal the speed of light. An object at or below this radius, Michel reasoned, would prevent light from escaping. It would be invisible, detectable only through its gravitational influence on nearby objects. He called these hypothetical objects dark stars. In 1796, the French mathematician and astronomer Pierre-Simon Laplace independently arrived at the same conclusion in his exposition Du Système du Monde. Both Michel and Laplace were working within a Newtonian framework that treats light as particles subject to gravitational force, a conceptually different approach from the general relativistic account of black holes. But the radius they calculated for what we now call the Schwarzschild radius matches the modern answer exactly. A striking result that reflects the way the same escape speed scale reappears in the relativistic solution, even though the underlying physical interpretation is different. The modern theory of black holes is built on Einstein's general theory of relativity, published in November 1915. General relativity describes gravity not as a force acting between masses, as Newton had conceived it, but as the curvature of space-time produced by mass and energy. In general relativity, massive objects distort the fabric of space-time around them, and other objects follow the straightest possible paths, geodesics, through this curved space-time, which appear to us as the curved trajectories of gravity. The warping of spacetime by a sufficiently massive and compact object can become so extreme that all geodesics within a certain radius converge on a central point, the singularity, producing what we recognize as a black hole. The key insight is that it is spacetime itself that is curved, not simply the paths of particles through an otherwise flat background. This makes black holes fundamentally different conceptually from dark stars. A dark star in the Newtonian picture is simply a star so massive and dense that its gravitational pull overcomes the kinetic energy of outgoing light, while a black hole in general relativity is a region in which spacetime itself is so curved that there are no outward-pointing geodesics, no directions that lead away from the singularity. The first exact solution to Einstein's field equations describing a black hole was found by German physicist Karl Schwarzschild in December 1915, barely a month after Einstein published the general theory of relativity, while Schwarzschild was serving on the Eastern Front during the First World War. He submitted his solution to Einstein in a letter from the front, and Einstein presented it to the Prussian Academy of Sciences on Schwarzschild's behalf in January 1916. The Schwarzschild solution describes the spacetime geometry outside a perfectly spherical, non-rotating, electrically neutral mass, and it contains a mathematical singularity at what is now called the Schwarzschild radius, the radius at which the event horizon of a black hole of a given mass is located. For an object with the mass of the Sun, the Schwarzschild radius is approximately 3 kilometers. For Earth, it would be approximately 9 millimeters, a sphere smaller than a marble. Schwarzschild died in May 1916 from illness contracted at the front, just months after his extraordinary contribution to theoretical physics. For several decades after Schwarzschild's solution, physicists debated whether the singularity at the Schwarzschild radius was a genuine physical feature of spacetime or merely an artifact of the particular coordinate system Schwarzschild had used. In 1933, Belgian physicist Georges Lemaitre showed that the singularity at the event horizon was a coordinate singularity, a mathematical artifact that disappeared with a change of coordinates, while the singularity at the center was a genuine curvature singularity. The physical reality of the event horizon was further clarified by David Finkelstein in 1958, who provided a clear physical interpretation of the Schwarzschild radius as a one-way membrane. Events outside this surface can still fall inward and affect the region inside, while events inside cannot send signals back out to the exterior universe. The term black hole itself was popularized by physicist John Archibald Wheeler in 1967, replacing the earlier terms frozen star and collapsar. Wheeler was the primary figure in the mid-20th century revival of interest in general relativistic objects, including black holes, and his vivid terminology helped establish them as a central focus of theoretical physics research. Black holes form through several distinct mechanisms, the best understood of which is the collapse of massive stars at the end of their lives. When a star with a mass greater than approximately 20 to 25 times the mass of the Sun exhausts the nuclear fuel in its core, the thermal pressure that has supported the star against gravitational collapse is suddenly removed. The core collapses catastrophically in a fraction of a second, and if the resulting object exceeds the maximum mass that a neutron star can support, the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses, the collapse continues without any known mechanism capable of halting it, and a black hole forms. The outer layers of the star are typically expelled in a supernova explosion, though in some cases the entire star may collapse directly without a visible supernova. The black hole that forms from this process is a stellar mass black hole, typically between approximately 5 and 100 solar masses, and is the type most commonly discussed in the context of stellar evolution. Supermassive black holes are a qualitatively different category. objects with masses ranging from approximately 100,000 to tens of billions of solar masses, found at the centers of virtually every large galaxy, including our own Milky Way. The mechanism by which supermassive black holes form and grow is not fully understood and represents one of the most active areas of research in observational and theoretical astrophysics. The leading theories propose that supermassive black holes grew from seed black holes, either the remnants of the first generation of massive stars, or black holes formed directly from the collapse of large gas clouds in the early universe, that then accreted mass over billions of years through the gravitational capture of gas and the merging of smaller black holes. The challenge for this picture is explaining how black holes of billions of solar masses could have grown in the first billion years of the universe. Observational evidence shows quasars powered by supermassive black holes already existing when the universe was less than 1 billion years old, and growing from a stellar mass seed to billions of solar masses in that time requires sustained near-Eddington accretion that is difficult to achieve. Intermediate mass black holes, with masses between approximately 100 and 100,000 solar masses, represent a theoretically predicted but observationally elusive class. They would fill the gap between stellar mass black holes and supermassive black holes, and their existence is predicted by several theories of black hole growth, including the runaway merging of massive stars in dense star clusters. Several candidate intermediate mass black holes have been identified through various methods, including the behavior of ultraluminous X-ray sources and the properties of certain globular clusters, but none has been confirmed with the certainty that accompanies the identification of stellar mass and supermassive black holes. The detection of gravitational waves from merging black holes in the mass range of several hundred solar masses by the LIGO and Virgo detectors has provided some of the more compelling evidence for the existence of this intermediate category. The event horizon is the defining boundary of a black hole, but it is worth emphasizing again how conceptually unusual it is. It has no material existence. It is not a surface in the sense of having any physical substance, texture, or property. A particle crossing the event horizon of a sufficiently large black hole would not necessarily experience anything unusual at the moment of crossing. Locally, the physics at the event horizon is smooth and regular because the curvature there, while extreme, is finite for a large enough black hole. The strangeness of the event horizon is global rather than local. It is the property that makes it a boundary of no return, not any local physical peculiarity. For a black hole of stellar mass, tidal forces at the event horizon would be enormous and destructive. But for a supermassive black hole of billions of solar masses, the event horizon radius is so large, billions of kilometers, that tidal forces there are relatively gentle. A hypothetical traveler falling into such a black hole would cross the event horizon without any dramatic immediate signal, noticing only gradually, over time, that the apparent center of gravity had moved from outside to inside their trajectory and that the universe behind them was becoming a shrinking window. The singularity at the center of a black hole represents the breakdown of general relativity. In the Schwarzschild solution, the singularity is a point at which the curvature of spacetime becomes infinite. All geodesics terminate there, and the mathematical equations that describe spacetime produce meaningless results. Most physicists interpret this not as a physical infinity, but as a signal that general relativity is incomplete, that a quantum theory of gravity, which reconciles general relativity with quantum mechanics, would provide a different and finite description of what happens at the Planck scale near the center of a black hole. The singularity, on this view, is not real but is an artifact of applying a classical theory in a regime where quantum effects dominate. What actually happens in the deep interior of a black hole, near the singularity, is genuinely unknown and represents one of the frontiers where theoretical physics is most actively seeking new understanding. The no-hair theorem, established in the 1960s and 1970s through the work of Werner Israel, Brandon Carter, David Robinson, and Stephen Hawking, states that black holes can be completely described by only three parameters: their mass, their electric charge, and their angular momentum, or spin. All other information about the matter that formed the black hole, its composition, its temperature, its structure, is lost when it crosses the event horizon. This is sometimes expressed as black holes have no hair, meaning they retain none of the detailed structure of their formation history. The theorem is a mathematical result within classical general relativity, and it has important implications for the information paradox and for the thermodynamics of black holes. The elegant simplicity of a black hole, fully characterized by just three numbers, is one of the more striking features of these objects in classical theory, in contrast to the extraordinary complexity of the stars and matter that forms them. The rotation of a black hole produces one of the more extraordinary phenomena in general relativity, frame dragging, or the Lentz-Thirring effect, in which a rotating mass drags the surrounding spacetime around with it, like a rotating marble dragging the surface of a cloth. For a sufficiently rapidly rotating black hole, described by the Kerr solution to Einstein's equations, published by Roy Kerr in 1963, this frame dragging becomes extreme, producing a region around the black hole called the ergosphere, in which spacetime itself is dragged so rapidly that it is impossible for any object, even a photon, to remain stationary with respect to distant observers. The ergosphere lies outside the event horizon, and objects within it are forced to rotate with the black hole, but can still escape because they are outside the event horizon. The Penrose process, proposed by Roger Penrose in 1969, describes how energy can in principle be extracted from a rotating black hole through interactions within the ergosphere, with a particle splitting into two parts, one of which falls into the black hole on a negative energy trajectory and the other escaping with more energy than the original particle had, the difference coming from the rotational energy of the black hole. In real astrophysical systems, the most important energy extraction mechanisms are thought to be electromagnetic rather than simple particle splitting processes, especially the Blandford-Znajek mechanism. But the Penrose process revealed the deep idea that a rotating black hole is not merely a sink. It is also, under the right conditions, an enormous reservoir of extractable rotational energy. The first horizon-scale image of a black hole shadow was captured and released to the public in April 2019 by the Event Horizon Telescope Collaboration, an international network of radio telescopes spread across the Earth that collectively functioned as a single telescope with an effective aperture the size of the planet. The image showed the supermassive black hole at the center of the galaxy M87, located approximately 55 million light-years from Earth and estimated to weigh approximately 6.5 billion solar masses. The image revealed a bright ring of emission, hot gas falling into the black hole, heated and brightened as it spirals inward, surrounding a dark central region, the shadow of the black hole, where the emission is suppressed by the black hole's gravity. The image was consistent with the predictions of general relativity for the appearance of a black hole of this mass and distance. In 2022, the Event Horizon Telescope Collaboration released the first image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way, a more technically challenging observation because Sagittarius A star is much smaller and more variable than M87 star, requiring special techniques to handle the variability during the hours-long observations. Sagittarius A star, at the center of the Milky Way approximately 26,000 light-years from Earth, has a mass of approximately 4 million solar masses. Its existence was established over decades of careful observation of the orbits of stars in the galactic center, carried out primarily by teams led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany and Andrea Ghez at UCLA, both of whom shared the 2020 Nobel Prize in Physics for this work with Roger Penrose, who received the other half of the prize for his theoretical work on black holes. The star designated S2 orbits Sagittarius A star with a period of approximately 16 years and a closest approach of approximately 120 astronomical units, slightly larger than the distance from the Sun to the outer solar system, at which point it reaches a speed of approximately 3% of the speed of light. By tracking the orbits of S2 and other stars over multiple complete orbits, the mass and position of Sagittarius A star have been determined with extraordinary precision, providing one of the most compelling direct measurements of a supermassive black hole's properties. When matter falls into a black hole, it does not simply disappear cleanly. In most cases, infalling gas and material forms an accretion disk, a flattened, rotating structure of material spiraling inward under gravity, heated by viscous friction and electromagnetic effects to temperatures of millions of degrees, and emitting radiation across the electromagnetic spectrum, predominantly in X-rays. The luminosity of an actively accreting black hole can exceed the combined light output of all the stars in the surrounding galaxy, producing what we call active galactic nuclei, or quasars, when the accretion is especially vigorous. The most luminous quasars release energy at rates exceeding 10 trillion times the luminosity of the Sun. This extraordinary luminosity comes from the gravitational energy liberated as matter falls into the black hole's potential well. The efficiency with which rest mass can be converted to radiation through accretion onto a black hole can, in idealized models of rapidly rotating black holes, approach roughly 40%, compared with less than 1% of mass converted to energy in ordinary hydrogen fusion in stars. This extraordinary efficiency makes black hole accretion the most energetically powerful process in the universe above subatomic scales. The jets produced by actively accreting black holes, collimated streams of plasma ejected perpendicular to the accretion disk at velocities approaching the speed of light, are among the most powerful and most spatially extensive structures in the universe. The mechanism by which these jets are formed and collimated is not fully understood, but the leading model involves the extraction of rotational energy from either the spinning black hole itself, through the Blandford-Znajek mechanism, or from the inner regions of the accretion disk, through the Blandford-Payne mechanism. Jets from supermassive black holes in active galactic nuclei can extend for millions of light years, far beyond the confines of the host galaxy, depositing enormous amounts of energy into the intergalactic medium and influencing the evolution of galaxies on vast scales. The jet from M87, now imaged at its base by the Event Horizon Telescope, extends approximately 5,000 light-years from the galactic center and is one of the most thoroughly studied astrophysical jets in the sky. Gravitational waves from merging black holes were first detected in September 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, in what was one of the most celebrated experimental discoveries in the history of physics. The signal, designated GW150914, was produced by the merger of two stellar mass black holes, approximately 36 and 29 solar masses respectively, located approximately 1.3 billion light-years from Earth, and the entire in-spiral, merger, and ring-down lasted less than a quarter of a second in the detector data. The gravitational wave signal stretched and compressed the Earth by an amount smaller than 1/10,000th of the diameter of a proton, yet the LIGO detectors, among the most sensitive measurement instruments ever constructed, detected it clearly. The discovery confirmed a key prediction of general relativity and opened an entirely new observational window on the universe, gravitational wave astronomy, that complements electromagnetic observation by detecting events that are otherwise invisible. The Nobel Prize in Physics for 2017 was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their contributions to LIGO and the detection of gravitational waves. The black hole information paradox is one of the deepest and most long-standing unsolved problems in theoretical physics, sitting at the intersection of quantum mechanics and general relativity. It arises from a tension between two fundamental principles: the principle of unitarity in quantum mechanics, which holds that quantum evolution is reversible and that information about the initial state of a system is always conserved, even if encoded in an apparently complicated or inaccessible form, and the properties of black holes in classical general relativity, which appear to destroy information irreversibly when matter falls into the singularity and the black hole eventually evaporates. Through Hawking radiation, if information is genuinely destroyed, unitarity is violated, undermining the foundations of quantum mechanics. If information is somehow preserved, encoded in the Hawking radiation emitted as the black hole evaporates, then the mechanism by which this occurs must involve non-local or otherwise exotic physics that challenges our current understanding of spacetime. The paradox has driven some of the most innovative theoretical physics of the past 50 years, including the holographic principle, the firewall hypothesis, and the island formula, but a fully satisfying resolution remains elusive. Stephen Hawking's 1974 prediction that black holes should emit thermal radiation, now called Hawking radiation, combined quantum field theory with the curved spacetime of general relativity in a way that had never been done before and produced a profoundly surprising result. In quantum field theory, the vacuum is not truly empty but seeds with pairs of virtual particles and antiparticles that briefly appear and annihilate. A popular way to picture the result is to imagine one member of a virtual pair falling inside the event horizon while the other escapes to infinity. But the real calculation is subtler. Quantum fields defined on a spacetime with a horizon make the vacuum seen by a distant observer look like a faint thermal glow. The escaping radiation behaves as if the black hole has a temperature. This radiation has a thermal spectrum corresponding to a temperature inversely proportional to the mass of the black hole. A black hole with the mass of the Sun would have a Hawking temperature of roughly 60 nanokelvin, and a black hole several times the mass of the Sun would be even colder, far below the temperature of the cosmic microwave background and utterly undetectable with any current instrument. Much smaller hypothetical black holes would be far hotter, and the tiny primordial black holes light enough to be in their final stages of evaporation today would release intense radiation, but no such evaporation has ever been observed. No black hole formed by ordinary astrophysical processes has ever been observed to evaporate, and the Hawking temperature of any known black hole is so low that detecting the radiation is entirely beyond current technology. Nevertheless, Hawking radiation is widely regarded as one of the most important and robust semi-classical predictions in gravitational physics, even though its direct detection from an astrophysical black hole remains far beyond present technology. The entropy of a black hole, a concept introduced by Jacob Bekenstein in 1972 and given precise form by Hawking, is proportional to the area of the event horizon, not its volume. This is an extraordinary statement. For ordinary matter, entropy is an extensive quantity proportional to volume. For a black hole, it is proportional to the two-dimensional surface area of the horizon. The Bekenstein-Hawking entropy formula states that the entropy of a black hole equals 1/4 of the event horizon area measured in units of the Planck area, where the Planck area is the square of the Planck length. approximately 10 to the power of minus 66 square centimeters, the scale at which quantum gravitational effects become important. The entropy of a typical stellar mass black hole is approximately 10 to the power of 77 in natural units, an almost incomprehensibly large number, larger than the entropy of the Sun or any other known physical system. The connection between entropy and horizon area has had profound theoretical consequences, suggesting that the information content of a three-dimensional volume of spacetime may somehow be encoded on its two-dimensional boundary, an idea that became the holographic principle. The holographic principle, proposed by Gerard T. Hooft and Leonard Susskind in the early 1990s, proposes that all the information needed to describe the physics within a volume of space is encoded on the two-dimensional boundary of that region, like a hologram in which a three-dimensional image is encoded on a two-dimensional surface. This radical idea was inspired by the Bekenstein-Hawking entropy formula and by the black hole information paradox, and it found its most precise and productive expression in the anti-de-Sitter/conformal field theory correspondence, or ADS/CFT duality, proposed by Juan Meldacena in 1997. The ADS/CFT correspondence is a mathematical equivalence between a theory of gravity in a specific type of curved spacetime, anti-de Sitter space, and a quantum field theory without gravity on the lower dimensional boundary of that spacetime. While the applicability of this specific correspondence to our universe is debated, the broader idea that it instantiates that quantum gravity in three spatial dimensions is equivalent to a quantum theory without gravity in two dimensions has been enormously productive and has influenced approaches to quantum gravity, condensed matter physics, and quantum information theory. The holographic principle, if it is correct, would represent one of the most fundamental insights into the nature of space-time and information in the history of physics. The firewall paradox, proposed by Ahmed Al-Mahiri, Donald Merolf, Joseph Polchinski, and James Sully in 2012, collectively known as AMPS, sharpened the black hole information paradox in a dramatic way. The AMPS argument showed that three reasonable-seeming assumptions about black holes and quantum mechanics are mutually inconsistent. The principle that an infalling observer experiences nothing unusual at the event horizon. The principle that information is preserved and escapes in Hawking radiation. And the principle that quantum field theory works normally outside the horizon. The combination of these three principles leads to a logical contradiction. To avoid the contradiction, AMPS proposed that the event horizon is not the smooth, unexceptional boundary of classical general relativity, but rather a wall of high-energy quanta, a firewall, that would incinerate any infalling observer. This proposal was controversial because it appeared to violate the equivalence principle, one of the cornerstones of general relativity. The firewall paradox has generated enormous theoretical activity, including the proposal by Juan Meldacena and Leonard Susskind that the entanglement between a black hole and its Hawking radiation is equivalent to wormholes connecting the interior and exterior of the black hole. Their E(r) equals EP are conjecture, but a fully satisfying resolution of the paradox remains an open problem. Primordial black holes are a hypothetical class of black holes that could have formed in the early universe from density fluctuations before the first stars were born, rather than from stellar collapse. They have attracted renewed interest in recent decades as a possible component of dark matter, the invisible substance that makes up approximately 27% of the universe's mass energy content. If primordial black holes exist in the right mass range, they could collectively account for some or all of the dark matter without requiring any new fundamental particles. The mass range for which primordial black holes could constitute the dark matter is constrained by various observations. Too light, and they would have evaporated by now through Hawking radiation. Too heavy, and they would produce observable signatures in gravitational lensing surveys or in the orbital dynamics of stars, but a window in the asteroid mass range remains open. The gravitational wave signals detected by LIGO and Virgo include events involving black holes more massive than expected from ordinary stellar evolution, and some researchers have proposed that these could be primordial black holes, though ordinary astrophysical explanations are generally preferred. The tidal forces near a black hole produce one of the more dramatic effects associated with black hole physics, spaghettification. As an object falls toward a black hole, the difference in gravitational force between the side of the object closer to the black hole and the side farther away produces a stretching force along the radial direction and a compressive force perpendicular to it. For a stellar mass black hole, these tidal forces become enormous even before the event horizon is reached, stretching any infalling object into a long, thin stream, hence the informal term spaghettification. For a supermassive black hole, the tidal forces at the event horizon are much weaker because the event horizon is much further from the singularity. A human falling into a supermassive black hole would not be spaghettified at the horizon. The tidal forces there would be comparable to those near the Earth. Tidal disruption events. Observations of stars being torn apart by the tidal forces of supermassive black holes when they pass too close to the galactic center are detected several times per year by wide-field transient surveys, and they provide some of the most dramatic direct evidence for the presence of supermassive black holes in the centers of galaxies. The shadow of a black hole, the dark region at its center in images like those produced by the Event Horizon Telescope, is not simply the black hole itself, but a region of approximately 2.5 times the Schwarzschild radius from which photons cannot escape to a distant observer. Photons on circular orbits exist precisely at the photon sphere at a radius of 1.5 times the Schwarzschild radius for a non-rotating black hole. Just outside the photon sphere, photons can orbit but are unstable. Any small perturbation will cause them to either fall inward or escape outward. The photon sphere has observable consequences. Photons emitted from just outside it can orbit the black hole multiple times before escaping, producing a series of increasingly dim and increasingly compressed rings in the black hole image. The Event Horizon Telescope images of M87 star and Sagittarius A star show the bright ring of emission from near the photon sphere, with the dark shadow within it, consistent with the predictions of general relativity for black holes of their respective masses. Wormholes, hypothetical tunnels through space-time connecting distant regions, are related to black holes in theoretical physics in ways that have become increasingly profound. Einstein and Rosen described in 1935 what is now called an Einstein-Rosen bridge, showing that the full mathematical extension of the Schwarzschild black hole solution contains two asymptotically flat regions of spacetime connected by a narrow throat, a wormhole. This Einstein-Rosen bridge is not traversable. The two regions are moving apart faster than light can travel through the throat, and anything attempting to pass through the wormhole from one side to the other would be forced to turn around before reaching the other region. Traversable wormholes, wormholes through which matter could travel in both directions, require exotic matter with negative energy density to hold the throat open. And while such exotic matter is not known to exist in nature, it is not ruled out by fundamental physics. The ER equals EP are conjecture of Meldesena and Susskind, mentioned earlier, proposed that quantum entanglement between distant particles is equivalent to a microscopic wormhole connecting them, suggesting a deep connection between the non-local correlations of quantum mechanics and the geometric structure of spacetime. Hawking radiation, if it exists and if information is preserved in it, must encode in the outgoing radiation an extraordinarily complicated record of everything that fell into the black hole. The mechanism by which this information encoding occurs is deeply mysterious. The photons making up the early Hawking radiation must be quantum mechanically entangled with the photons making up the late Hawking radiation in a highly specific way that encodes the infalling information. But any attempt to see where and how this entanglement is established seems to lead to contradictions with either local physics at the horizon or with the unitarity of quantum mechanics. The recent calculation by Pennington, Almhiri, Mahajan, Meldesena, and Zhao using the island formula, a new approach to computing entropy in gravitational theories developed in 2019, reproduces what is called the Page curve, the expected behavior of entropy in a unitary quantum system undergoing evaporation, suggesting that information is indeed preserved in Hawking radiation. But the mechanism by which this occurs in physical spacetime remains mysterious. The island formula works as a mathematical prescription, but does not yet provide a clear physical picture of where the information is and how it gets out. The cosmic censorship conjecture, proposed by Roger Penrose in 1969, states that singularities formed by gravitational collapse are always hidden inside event horizons, that naked singularities visible to distant observers without an event horizon shielding them, do not form in nature. This conjecture is physically significant because a naked singularity would represent a breakdown of the predictability of general relativity, a point from which arbitrary amounts of radiation could emerge, making future evolution of the spacetime unpredictable. The conjecture has been the subject of intense theoretical investigation. Counterexamples involving exotic initial conditions have been constructed mathematically, and there is evidence that certain types of highly fine-tuned collapse can produce naked singularities. But the consensus among general relativists is that for generic, realistic initial conditions, cosmic censorship holds, that nature hides its singularities. The proof of cosmic censorship for generic initial conditions remains one of the major open problems in mathematical general relativity. The merger of two black holes, as observed through gravitational waves, produces a final black hole that briefly rings like a bell, a phenomenon called ring-down. Immediately after the merger, the distorted new black hole emits gravitational waves at specific frequencies and damping rates, called quasi-normal modes, that are determined entirely by the mass and spin of the final black hole, in accordance with the no-hair theorem. By measuring the frequency and damping rate of the ring-down signal, it is possible in principle to test the no-hair theorem directly. If the measured quasi-normal modes are consistent with the predictions for a Kerr black hole, the general relativistic solution for a rotating black hole, this provides evidence that the merged object really is a Kerr black hole, as predicted. The LIGO and Virgo data from the first few detections provided the first tests of the no-hair theorem through ring-down measurements. And while the statistical precision of these early tests was limited by the signal-to-noise ratio of the detections, future gravitational wave detectors of higher sensitivity will perform increasingly precise tests of the Kerr hypothesis. The detection of gravitational waves from black hole mergers has revealed a population of black holes whose masses span a much wider range than anticipated from stellar evolution models. Several events detected by LIGO and Virgo involve black holes more massive than expected. The merger event GW190521, for example, involved progenitor black holes of approximately 85 and 66 solar masses, and produced a final black hole of approximately 142 solar masses, squarely in the intermediate mass range thought to be unpopulated by ordinary stellar collapse, because pair instability supernovae are expected to prevent the formation of black holes in a broad mass interval, often described as an upper mass gap, whose exact boundaries depend on stellar models. The origin of these massive black holes is debated, with proposals including hierarchical mergers in dense environments, primordial black holes, and stellar evolution in unusual conditions. Black holes do not actively pull in material from a distance. The common misconception that a black hole acts as a cosmic vacuum cleaner, drawing in material from far away, is inaccurate. The gravitational field of a black hole at a given distance is no stronger than that of any other object of the same mass at the same distance. A black hole of one solar mass, if one were to replace the Sun, would exert the same gravitational force on the Earth as the Sun does now. The Earth would continue to orbit it undisturbed, in exactly the same orbit. Material falls into a black hole only if it comes close enough that it cannot maintain a stable orbit, that is, closer than the innermost stable circular orbit, which lies at 3 times the Schwarzschild radius for a non-rotating black hole. Outside this distance, stable circular orbits exist, and material can orbit indefinitely without spiraling inward. It is only within the innermost stable circular orbit that orbital energy is lost faster than it can be replaced, and infalling is inevitable. The relationship between black holes and time is one of the more conceptually challenging aspects of the subject. Because time is part of spacetime and spacetime is curved by gravity, the rate at which time passes varies with position in a gravitational field, a phenomenon called gravitational time dilation. Clocks close to a massive object run slower than clocks far away, as measured by a distant observer. Near the event horizon of a black hole, this time dilation becomes extreme. From the perspective of a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, its light becoming increasingly redshifted and dim, and in the limit of reaching the event horizon, it appears to freeze, never quite crossing. The object never appears to cross the event horizon from the external observer's perspective, though from the infalling object's own perspective, it crosses the horizon in finite proper time, and then reaches the singularity in finite proper time after that. These two perfectly consistent descriptions of the same event, the object freezes at the horizon and never crosses from outside. The object crosses the horizon and reaches the singularity from inside, are the result of the two observers simply being in different reference frames, each of which gives a valid description of the events from their own perspective. The possibility of black holes evaporating completely through Hawking radiation raises the question of what happens to the spacetime region that was inside the event horizon. In the standard picture, as a black hole loses mass through Hawking radiation, its Schwarzschild radius decreases and the event horizon shrinks. The final stage of evaporation, when the black hole is very small and very hot and the Hawking radiation is very intense, is in a regime where quantum gravity effects dominate and classical general relativity cannot be trusted. Whether the final state is a Planck scale remnant, a naked singularity, complete evaporation into radiation, or something entirely outside current theoretical frameworks is not known. The final evaporation of a black hole, if it occurs, remains one of the most genuinely mysterious processes in theoretical physics. The Penrose process, mentioned earlier, is one specific mechanism for extracting energy from a rotating black hole. The broader class of processes by which rotational energy can be extracted is important for understanding the energetics of active galactic nuclei and gamma-ray bursts. A rotating black hole is characterized not only by its mass, but by its dimensionless spin parameter, ranging from 0 for a non-rotating Schwarzschild black hole to 1 for a maximally rotating Kerr black hole, the theoretical limit at which the equatorial surface of the event horizon would be moving at the speed of light. The energy associated with this maximum rotation is approximately 29% of the total mass energy of the black hole, an enormous reservoir that can be tapped by processes within the ergosphere. The extraction of this rotational energy spins the black hole down towards 0, and the theoretical endpoint of continued energy extraction from a maximally rotating black hole is a Schwarzschild black hole with a mass slightly less than the original Kerr black hole, but with approximately 29% of its mass energy converted to radiation and jets. The center of the Milky Way, where Sagittarius A star resides, is a region of extraordinary activity and violence by the quiet standards of the surrounding galaxy. The central few light years contain a dense cluster of young and massive stars, the S star cluster, whose presence so close to the supermassive black hole is one of the puzzles of galactic center astronomy, since forming such stars in the extreme tidal environment of the galactic center is theoretically very difficult. There are also older stars on long elliptical orbits, streams of hot ionized gas, X-ray binaries, and magnetars, all in an environment pervaded by strong magnetic fields, elevated cosmic ray densities, and proximity to one of the most massive objects in the local galaxy. Despite all this, Sagittarius A star is currently in a relatively quiet state, accreting mass at a rate far below its maximum. It shows occasional flares in X-ray and infrared emission, lasting minutes to hours, that indicate brief episodes of enhanced accretion, but nothing approaching the luminosity of an active galactic nucleus. The contrast between the current quiet state of Sagittarius A star and the energetic events of the distant past, the Fermi bubbles extending 25,000 light-years above and below the galactic plane, believed to have been inflated by a past active phase, suggests that our galaxy's central black hole was once far more active and may become so again in the future. The study of black holes has generated some of the most important and most beautiful mathematics in theoretical physics of the past century. The Kerr solution, describing a rotating black hole, required mathematical techniques developed by Kerr from deep in the theory of algebraically special spacetimes. The singularity theorems proved by Penrose and Hawking in the 1960s and 1970s, establishing that singularities are unavoidable in gravitational collapse under very general conditions, used topological methods from differential geometry, Penrose's theorem of 1965 being the first use of what are now called topological methods in general relativity. The entropy and thermodynamics of black holes, Hawking radiation, and the information paradox have drawn on and contributed to quantum field theory in curved spacetime, the theory of quantum information, and string theory. The ADS/CFT correspondence, developed to understand the holographic principle in the context of black hole physics, has become one of the most productive tools in theoretical physics, with applications extending far beyond its origins to include superconductivity, nuclear physics, and quantum information theory. Black holes have served as the extreme testing ground where the limits of our best physical theories are most clearly exposed. The measurement of a black hole's mass through the orbital dynamics of nearby material is one of the most powerful tools in observational astronomy. For stellar mass black holes in binary star systems, where a black hole is paired with a companion star from which it is accreting mass, the mass can be determined from the orbital period and velocity amplitude of the companion, combined with constraints on the inclination of the orbit from X-ray light curve modeling. For supermassive black holes, the method of stellar orbits used at the Milky Way center works beautifully, but requires angular resolution achievable only for the nearest galactic centers. More broadly applicable is the method of stellar and gas dynamics, measuring the velocities of stars or gas in the central regions of a galaxy and fitting dynamical models to determine what central mass concentration is required to produce the observed kinematics. The tight correlations between supermassive black hole mass and the properties of the host galaxy, particularly the velocity dispersion of the galaxy's stellar bulge, the M-sigma relation, have been established through these dynamical mass measurements and provide indirect evidence for supermassive black holes in thousands of galaxies beyond our ability to spatially resolve their influence. The future of black hole observation is extraordinarily rich. The next generation of gravitational wave detectors, including the Einstein telescope in Europe and Cosmic Explorer in the United States, ground-based detectors with arm lengths of 10 to 40 kilometers compared to LIGO's 4 kilometers, are expected to detect enormous numbers of black hole mergers, potentially thousands per year, mapping the population of black holes across cosmic time with statistical precision currently impossible. The Laser Interferometer Space Antenna, a space-based gravitational wave detector to be operated by the European Space Agency, will be sensitive to lower-frequency gravitational waves from the mergers of supermassive black holes in galaxy mergers, events of extraordinary energy occurring at cosmological distances. The next generation of Event Horizon Telescope arrays, with additional stations added to the existing network, will produce images of black hole shadows with significantly higher angular resolution and dynamic range, enabling tests of general relativity in the strong field regime with precision that current images cannot match. Pulsar timing arrays, monitoring dozens of pulsars across the galaxy as a gravitational wave detector sensitive to nanohertz frequencies, have already produced the first evidence for a stochastic gravitational wave background consistent with the expected signal from a cosmic population of supermassive black hole binaries. The era of multi-messenger astronomy, in which gravitational waves and electromagnetic observations are combined to study the same events, is already producing science that neither observation alone could achieve, and this combination will become increasingly powerful over the coming decades. The first strong candidate for a black hole in our own galaxy was Cygnus X1, an intense X-ray source in the constellation Cygnus. It was discovered in the 1960s during the early era of X-ray astronomy, when detectors above Earth's atmosphere first revealed a sky filled with high-energy objects invisible to ordinary telescopes. Cygnus X1 is a binary system, a massive blue supergiant star orbiting an unseen compact companion. Gas from the star is pulled toward the compact object, forming an accretion disk that becomes so hot it shines in X-rays. The invisible object is far too massive to be a neutron star, and it emits no light of its own. Over decades of observation, its mass, orbit, and radiation have made it one of the classic cases for a stellar mass black hole. The story matters because black holes were not accepted instantly as real astrophysical objects. They had to be recognized indirectly through the disciplined accumulation of effects, orbital motion, X-ray emission, mass estimates, and the absence of any ordinary object capable of explaining them. The distinction between a black hole and a neutron star depends on how matter responds under extreme compression. A white dwarf is supported by electron degeneracy pressure, a quantum mechanical resistance to compressing electrons into the same states. A neutron star is supported largely by neutron degeneracy pressure and nuclear forces, after electrons and protons have been squeezed together into neutrons. But even neutron stars have limits. If the mass of the collapsed core is too great, no known pressure can hold the object up against gravity. The collapse continues past every familiar form of matter, past atomic structure, past nuclear density, into a region where general relativity predicts an event horizon. This sequence, white dwarf, neutron star, black hole, is one of the most elegant demonstrations that gravity is not merely a weak force in everyday life, but the final authority in the lives of stars. When all other sources of pressure fail, geometry wins. The density of a black hole can be misleading because the event horizon grows in proportion to mass, while volume grows with the cube of radius. A stellar mass black hole compresses several suns into a region only a few tens of kilometers across, producing an average density vastly beyond ordinary matter. But a supermassive black hole can have an average density, calculated inside the event horizon, lower than the density of water, and for the most massive known black holes, even lower than the density of air. This does not mean the interior is gentle or ordinary. It means that the event horizon of a supermassive black hole is enormous. The larger the black hole, the less extreme the curvature at the horizon itself, even though the singularity deep inside remains beyond classical description. This is one of the reasons supermassive black holes are so strange. They can be unimaginably massive and yet, at their horizons, locally less violent than smaller black holes. There is a useful way to think about the Schwarzschild radius. For every solar mass of material compressed into a non-rotating black hole, the event horizon radius is about 3 kilometers. A black hole with 10 solar masses has a Schwarzschild radius of about 30 kilometers. A black hole with 4 million solar masses, like Sagittarius A star, has a radius of roughly 12 million kilometers. A black hole with 6.5 billion solar masses, like M87 star, has a horizon larger than the orbit of Pluto in scale. The formula is simple, but its implications are not. Gravity does not need a special substance to make a black hole. It needs mass packed inside a small enough radius. The event horizon is not made of matter. It is the place where the mass energy inside has changed the causal structure of spacetime so completely that future-directed paths no longer lead outward. The idea that nothing can escape a black hole must be understood carefully. Matter and light cannot escape once they are inside the event horizon, but black holes can still influence the outside universe gravitationally, electromagnetically through their surrounding plasma, and through gravitational waves produced by their motion and mergers. A black hole is not isolated from the cosmos in every sense. It is causally sealed only with respect to signals from inside the horizon. Its mass curves spacetime outside. Its spin can shape magnetic fields and accretion flows outside. Its motion can disturb spacetime across cosmic distances. The hole itself is dark, but the environment around it can be among the brightest places in the universe. This is why black holes are paradoxical observational objects. The central region emits nothing, yet the process is driven by matter approaching that region can outshine galaxies. Accretion disks around black holes are laboratories of extreme physics. Gas in an accretion disk does not fall straight inward because it almost always possesses angular momentum. Instead, it orbits, rubs against neighboring layers, heats through friction and turbulence, and gradually loses energy while preserving enough angular momentum to spiral inward rather than simply plunge. Magnetic fields threaded through the plasma amplify the turbulence, and the disk can reach temperatures high enough to emit X-rays. In the inner disk, orbital speeds approach a significant fraction of the speed of light. Light emitted from the approaching side of the disk is boosted and blue-shifted. Light from the receding side is dimmed and redshifted. The entire disk is warped visually by gravitational lensing. If the human eye could somehow survive and resolve it, an accretion disk would not look like a flat ring. It would look like a luminous structure bent around the darkness by spacetime itself. Not all accretion disks are efficient radiators. Some black holes, including Sagittarius A star in its present quiet state, appear to accrete matter inefficiently. Gas exists near them, but much of the gravitational energy is not converted into light before the material either falls inward or is blown away. These radiatively inefficient accretion flows are hot, tenuous, and magnetized, with particles that may not share a single common temperature. Electrons can radiate, ions can store energy, and outflows can remove mass before it reaches the horizon. This matters because a black hole's brightness does not simply tell us how massive it is. It tells us how much matter is falling in, how that matter is arranged, how magnetic fields behave, and how efficiently gravitational energy becomes radiation. A quiet black hole can be enormous. A smaller black hole can flare brilliantly. Darkness and mass are not the same thing. The Eddington limit is one of the key ideas in understanding black hole growth. As gas falls toward a black hole and heats up, the radiation it emits pushes outward on incoming matter. At a certain luminosity, radiation pressure balances gravity for ionized gas, creating a natural limit to how fast steady spherical accretion can proceed. This limit is not absolute. Disks, magnetic fields, geometry, and brief episodes of super Eddington accretion can complicate the picture, but it sets an important scale. The problem of early supermassive black holes is partly an Eddington problem. If a black hole begins as a small stellar remnant, there may not be enough time in the early universe for it to grow to a billion solar masses through ordinary steady accretion. This is why direct collapse black hole seeds, unusually massive first stars, and super Eddington growth episodes remain active areas of research. Quasars are the spectacular visible expression of feeding supermassive black holes. The word quasar originally meant quasi-stellar radio source, because the first examples looked star-like in optical telescopes, but had strange spectra and powerful radio emission. Once their redshifts were understood, astronomers realized they were not nearby stars at all, but extremely distant galactic nuclei, radiating with extraordinary luminosity. A quasar can shine across billions of light years because gas falling into its central black hole converts gravitational energy into radiation with tremendous efficiency. The light from some quasars has traveled for more than 12 billion years before reaching us, meaning we see them as they were when the universe was young. They are not only energetic objects, they are time machines, revealing the growth of black holes and galaxies near the beginning of cosmic history. Blazars are a special kind of active galactic nucleus in which one of the relativistic jets points nearly toward Earth. Because the jet is moving at a speed close to light speed, its radiation is relativistically beamed in our direction, making the object appear dramatically brighter and more variable than it would from another angle. Blazars can change brightness over days, hours, or even shorter timescales, which tells astronomers that the emitting region must be compact. Light cannot coordinate changes across a region larger than the distance it can cross during the observed variation time. This rapid variability, combined with emission across the electromagnetic spectrum from radio waves to gamma rays, makes blazars important laboratories for particle acceleration near black holes. Somewhere in those jets, plasma is being organized and accelerated by magnetic fields into beams extending far beyond the host galaxy. The relationship between black holes and galaxies is one of the deepest puzzles of cosmic structure. Supermassive black hole masses correlate with properties of their host galaxies, especially the velocity dispersion of stars in the central bulge. This suggests that black holes and galaxies grow together, influencing each other's evolution. But the direction of causality is not simple. A central black hole is tiny compared with its galaxy. Even a billion solar mass black hole is a small fraction of the stellar mass of a massive galaxy. Yet the energy released during accretion can heat or expel gas, suppress star formation, inflate bubbles in hot cluster gas, and regulate the growth of the galaxy. This feedback between black hole and galaxy is now considered essential in models of galaxy evolution. Without it, simulations often produce galaxies that are too massive, too blue, and too full of stars compared with the universe we observe. In galaxy clusters, supermassive black holes can shape environments on scales far larger than their host galaxies. The central galaxies of clusters often contain enormous black holes whose jets blow cavities into the surrounding hot X-ray emitting gas. These cavities can be hundreds of thousands of light years across. They are not empty in the everyday sense, but they are regions where jets have displaced the hot intracluster medium, doing mechanical work against it. This energy injection can prevent the hot gas from cooling rapidly and falling into the central galaxy to form new stars. The black hole therefore acts almost like a thermostat for the cluster core. When gas cools and feeds the black hole launches jets that heat the gas and reduce the fuel supply. The cycle is not perfectly steady, but it reveals a remarkable fact. An object defined by a boundary of darkness can regulate the thermal life of an entire cluster of galaxies. Tidal disruption events occur when a star passes close enough to a supermassive black hole that tidal forces overcome the star's own gravity. The star is stretched into a stream, with some material flung outward and some bound to the black hole. As the bound material falls back and circularizes into an accretion flow, it produces a flare of light that can be detected across vast distances. These events are rare for any single galaxy, but common enough across the observable universe that modern sky surveys find them repeatedly. They are valuable because they illuminate otherwise quiet black holes. A dormant supermassive black hole at the center of a galaxy may reveal itself only when an unlucky star wanders too close. For weeks, months, or years, the center of the galaxy brightens, and astronomers can study the mass, spin, accretion physics, and environment of a black hole that was previously invisible. The last stable orbit around a black hole is one of the most important boundaries outside the event horizon. For a non-rotating black hole, the innermost stable circular orbit lies at 3 Schwarzschild radii. Inside that radius, circular orbits are no longer stable, and matter tends to plunge inward. For a rotating black hole, the location of this orbit depends on spin and on whether matter orbits with or against the black hole's rotation. In the direction of spin, the innermost stable orbit can move closer to the horizon. Against the spin, it moves farther out. This matters observationally because the inner edge of an accretion disk leaves signatures in the disk spectrum. By measuring those signatures, astronomers can estimate black hole spin. Spin is not a minor detail. It stores energy, influences jet formation, and preserves clues about how the black hole grew. One of the main methods for estimating black hole spin uses the X-ray emission from hot accretion disks. In some systems, the disk extends close to the innermost stable circular orbit, and its thermal spectrum can be modeled to infer the radius of that inner edge. Another method uses the broad iron K-alpha emission line, produced when X-rays from the inner region illuminate iron atoms in the disk. Near the black hole, the line is broadened and skewed by Doppler shifts, gravitational redshift, and light bending. The shape of the line carries information about how close the emitting gas lies to the horizon, and therefore about spin. These measurements are difficult and model-dependent, but they are among the best tools available for probing the geometry of spacetime near the event horizon. The black hole itself is dark. Its spin is red from the glowing gas that barely avoids falling in. Gravitational lensing around black holes produces effects unlike lensing around ordinary stars or galaxies because the curvature is so strong near the photon sphere. Light from the far side of an accretion disk can be bent over the top of the black hole and reach the observer, making the disk appear to wrap around the shadow. Some photons can orbit the black hole one or more times before escaping, producing higher-order images, faint, compressed rings nested closer and closer to the edge of the shadow. These photon rings are extraordinarily difficult to observe, but they are of deep theoretical interest because their shape and size are determined primarily by the spacetime geometry. Future very long baseline interferometry, especially with telescopes in space, may one day resolve these structures more clearly. If that happens, black holes will become not only dark objects with bright rings, but precision tests of gravity written in light. The phrase black hole shadow is sometimes misunderstood. The shadow is not the event horizon photographed directly. The event horizon is smaller than the shadow. The shadow is the dark region on the sky caused by photons being captured by the black hole or strongly bent away from the observer. Its size depends on the photon capture region and the lensing of light near the black hole. This is why the Event Horizon Telescope did not photograph the surface of a black hole. It imaged millimeter wave emission from hot plasma near the horizon and measured the central brightness depression produced by the black hole's gravity. That distinction matters because it is precisely what makes the observation so powerful. We do not need to see a material surface. General relativity predicts the appearance of the shadow from spacetime geometry, and the observed ring sizes match that prediction. The polarization of light near black holes adds another layer of information. Light becomes polarized when its electric field oscillates preferentially in certain directions, and synchrotron radiation from electrons spiraling around magnetic field lines is naturally polarized. By measuring polarization in the ring around M87 star and Sagittarius A star, astronomers can infer the structure of magnetic fields close to the event horizon. These magnetic fields are not decorative details. They may determine how accretion flows behave, how jets launch, and how energy moves from a spinning black hole into surrounding plasma. The polarized images show that black holes are not merely gravitational objects, but magnetized engines. Around the darkness is a living electromagnetic environment, twisting and reorganizing under conditions that cannot be reproduced in any laboratory on Earth. Binary black holes are natural consequences of stellar evolution and galaxy evolution. Massive stars often form in pairs, and if both stars are massive enough, each can collapse into a black hole. Whether the resulting black holes merge depends on the history of mass transfer, supernova kicks, common envelope evolution, and orbital energy loss. In dense star clusters, black holes can also form binaries dynamically through close encounters, exchange interactions, and repeated mergers. These different formation channels leave different statistical fingerprints in the masses, spins, and orbital orientations of the merging black holes. Gravitational wave observatories do not merely detect individual mergers. They build a population catalog. Over time, the distribution of black hole masses and spins will reveal how massive stars die, how dense clusters evolve, and whether some black holes are second-generation objects formed from earlier mergers. A gravitational wave chirp is one of the simplest and most beautiful signals in astrophysics. As two black holes orbit each other, they emit gravitational waves that carry away energy and angular momentum. The orbit shrinks. The black holes move faster. The frequency of the gravitational waves rises. The amplitude rises as well. In the detector, the signal sweeps upward in pitch and strength before ending in merger and ring down. The word chirp is almost too small for the event it describes. Two horizons spiraling together, space-time itself vibrating. Several solar masses of energy radiated away as gravitational waves in a fraction of a second. Yet the waveform is mathematically precise. From the shape of the chirp, astronomers can infer the masses, spins, distance, and orientation of the system. A soundless event in deep space becomes a measurable pattern in laser light on Earth. Gravitational waves are not waves traveling through space in the ordinary sense. They are ripples in space-time itself, changing the distances between freely falling objects as they pass. A detector like LIGO measures this by comparing the lengths of two perpendicular arms using laser interferometry. When a gravitational wave passes, one arm is stretched slightly while the other is compressed, and then the pattern reverses. The change is unimaginably small, far less than the width of a proton over a 4-kilometer arm. Detecting it requires mirrors suspended so carefully they behave almost like freely floating test masses, lasers stabilized to extraordinary precision, seismic isolation, vacuum systems, and statistical analysis capable of distinguishing cosmic signals from terrestrial noise. The existence of such detectors is itself one of the quiet triumphs of human engineering. The first gravitational wave detection did more than confirm that black holes merge. It confirmed that black holes in the mass range of several tens of solar masses exist in binary systems and can coalesce within the age of the universe. Before that event, stellar mass black holes were known mainly from X-ray binaries, where they reveal themselves by accreting from companion stars. But gravitational waves revealed a hidden population, black holes that may be dark for their entire lives until the final fraction of a second before merger. These systems emit no light, no X-rays, no visible signal. They are discovered only when spacetime rings. This changed the observational meaning of black holes. They were no longer only electromagnetic objects inferred from glowing gas. They became gravitational objects observed directly through the motion of spacetime. The final black hole produced by a merger is less massive than the sum of the two original black holes. The missing mass has not disappeared. It has been radiated away as gravitational waves. In the first LIGO event, roughly 3 solar masses of energy were emitted in a fraction of a second. During that brief moment, the power output in gravitational waves exceeded the combined light output of all the stars in the observable universe, though almost none of that energy interacted with matter as it passed through space. Gravitational waves are extraordinarily weakly coupled to matter, which is why they can cross the universe almost unimpeded and why they are so difficult to detect. The universe can contain the most powerful event since the Big Bang, and it can pass through Earth with only a whisper of stretching in the mirrors of an interferometer. The population of black holes detected through gravitational waves includes surprises. Some are heavier than many models expected. Some have spins that are lower or differently oriented than simple isolated binary evolution might predict. Some events may involve black holes in the so-called mass gap between the heaviest neutron stars and the lightest black holes, raising questions about the boundary between neutron star and black hole formation. Others involve final black holes in the intermediate mass range, suggesting that repeated mergers may occur in dense environments. Each detection is both an event and a data point. As the catalog grows, individual mysteries become statistical patterns, and statistical patterns become constraints on stellar evolution, metallicity, star cluster dynamics, and cosmology. Black holes may help measure the expansion of the universe. Gravitational wave events can function as standard sirens, analogous to standard candles in astronomy. The waveform of a compact binary merger directly encodes its luminosity distance, independent of many assumptions used in traditional distance ladders. If the host galaxy or electromagnetic counterpart can be identified, astronomers can combine distance with redshift to estimate the Hubble constant. For binary neutron star mergers, light counterparts are often possible. For black hole mergers, electromagnetic counterparts are usually absent, but statistical methods can still associate events with galaxy catalogs. As detections accumulate, gravitational waves may provide an independent route into one of modern cosmology's major tensions: the disagreement between different measurements of the universe's expansion rate. The possibility of primordial black holes connects black hole physics to the earliest fractions of cosmic time. Ordinary stellar black holes cannot form before stars exist, but primordial black holes, if real, could have formed from overdense regions in the hot early universe. Their masses would depend on the horizon scale at the time of formation, meaning they could range from tiny black holes that evaporated long ago to much larger objects that survive today. Because they would not require stars, they could predate galaxies. The idea is attractive because it might explain dark matter or some unusual gravitational wave events, but observations constrain it strongly. Microlensing surveys, cosmic microwave background measurements, stellar dynamics, and Hawking evaporation limits all restrict how many primordial black holes can exist in different mass ranges. The result is not a simple yes or no, but a map of shrinking allowed windows. Microlensing is one of the methods used to search for compact dark objects, including possible primordial black holes. When a compact mass passes in front of a distant star, its gravity bends and magnifies the star's light, producing a characteristic brightening event. Unlike ordinary lensing by galaxies, microlensing does not usually produce resolvable multiple images. It produces a change in brightness over time. Surveys monitoring millions of stars can search for these events statistically. If dark matter were made mostly of compact objects in certain mass ranges, microlensing events would be more common than observed. The lack of such events in many surveys rules out primordial black holes as the dominant dark matter component across broad mass ranges. But not all masses are equally constrained, and the remaining possibilities keep the subject alive. Charged black holes exist as mathematical solutions, but astrophysical black holes are expected to carry little net electric charge. Matter in the universe is generally electrically neutral on large scales, and any significant charge on a black hole would attract opposite charges and repel like charges, quickly neutralizing itself. The Reissner-Nordstrom and Kerr-Newman solutions, describing charged and rotating charged black holes, are therefore more important theoretically than observationally. They reveal what Einstein's equations allow and provide simplified laboratories for studying horizons, inner horizons, and singularities. But the black holes astronomers observe are effectively described by mass and spin, with electric charge negligible. This is another example of the gap between mathematical possibility and astrophysical reality. The equations offer a family of solutions. The universe chooses the ones its plasma, stars, and galaxies can actually make. Rotating black holes contain not only an outer event horizon but, in the ideal Kerr solution, an inner horizon called a Cauchy horizon. Beyond it, the deterministic structure of spacetime becomes mathematically unstable. Tiny perturbations can be infinitely blue-shifted, producing what is called mass inflation. Many physicists expect the inner structure of realistic rotating black holes to differ drastically from the clean mathematical Kerr solution because real black holes are never perfectly isolated. They accrete particles, radiation, magnetic fields, and gravitational waves. Their interiors may be violently unstable. This is one of the reasons we should be cautious when diagrams show black holes as neat tunnels to other universes or pathways through ring singularities. The exact solutions are mathematically beautiful, but the interiors of real astrophysical black holes are almost certainly less friendly and less orderly. The phrase singularity theorem refers to one of the great conceptual achievements of 20th century physics. Before Penrose and Hawking, some physicists suspected that singularities might be artifacts of unrealistic symmetry. Perhaps they appeared only in perfectly spherical collapse and would disappear in more realistic cases. Penrose showed that under broad physical conditions, gravitational collapse leads inevitably to incomplete geodesics, a sign that spacetime itself breaks down. Hawking extended related reasoning to cosmology, showing that the Big Bang singularity also arises under broad assumptions in classical general relativity. These theorems do not tell us what physically exists at a singularity. Instead, they tell us that classical spacetime, as described by general relativity, cannot be the final story. The equations are not merely difficult at the singularity. They are declaring their own domain of validity exhausted. Black hole thermodynamics began as an analogy and became something much deeper. The area of a black hole's event horizon behaves like entropy. It never decreases in classical processes, just as entropy never decreases in ordinary thermodynamics. The surface gravity of a black hole behaves like temperature. The mass behaves like energy. At first, these parallels seemed formal, perhaps poetic. But Hawking's discovery that black holes radiate thermally made the temperature real. The analogy became physics. A black hole has entropy, temperature, and a thermodynamic life. This was shocking because black holes had been understood as perfect absorbers, objects that only swallow. Thermodynamics revealed them as systems with statistical properties, and quantum field theory revealed them as faint emitters. The darkest objects in the universe turned out to have a temperature. The Page curve is a way of describing how information should behave if black hole evaporation is compatible with quantum mechanics. At first, Hawking radiation appears thermal and uninformative, and the entanglement entropy between the radiation and the remaining black hole rises. But if the total process is unitary, that entropy cannot rise forever. After a time called the Page time, the radiation must begin to carry information about the black hole's internal state, and the entropy must decline until the black hole has evaporated completely and the final radiation state contains the information in a scrambled form. The island formula calculations reproduce this expected curve in certain gravitational models, which is a major theoretical breakthrough. But the physical interpretation remains difficult. The mathematics suggests that portions of the black hole interior are encoded in the radiation. How to translate that into ordinary spacetime language is still not settled. The black hole complementarity proposal was an earlier attempt to resolve the information paradox without violating what any observer can measure. From the viewpoint of an outside observer, information falling toward a black hole is somehow absorbed, scrambled, and eventually re-emitted in Hawking radiation from the horizon. From the viewpoint of an infalling observer, nothing special happens at the horizon, and the information continues inward. No single observer can witness both copies of the information, so perhaps there is no contradiction. This idea was elegant, but the firewall argument later challenged whether it can be fully consistent with quantum entanglement. The debate reveals a recurring feature of black hole physics. Many proposed resolutions sound plausible until the details of quantum information are applied, and then the horizon becomes a sharper and stranger place. The term soft hair refers to a proposal associated with Stephen Hawking, Malcolm Perry, and Andrew Strominger, suggesting that black holes may carry additional information in subtle gravitational or electromagnetic degrees of freedom associated with symmetries at infinity and at the horizon. The idea was motivated by the information paradox and by developments in the study of asymptotic symmetries in spacetime. Whether soft hair is enough to resolve the information paradox remains debated, and many physicists think it is not sufficient by itself. But it is an important example of how black holes force theorists to reconsider what counts as information in gravity. In ordinary systems, information is often imagined as located in matter fields. In gravity, information may also be stored in the geometry itself, in boundary degrees of freedom, and in correlations that are invisible to local measurements. Analog black holes can be created in laboratory systems where waves move through a medium that has an effective horizon. For example, sound waves in a flowing fluid can encounter a point beyond which the fluid moves faster than the speed of sound in that medium, preventing sound from escaping upstream. This acoustic horizon is not a gravitational black hole, but the mathematics of wave propagation near it can resemble the mathematics of fields near an event horizon. Researchers have used such systems to study analog versions of Hawking radiation. These experiments cannot prove that astrophysical black holes radiate, but they can test aspects of the underlying physics of horizons and quantum fields in effective spacetimes. They remind us that a horizon is not only a place in astronomy. It is a pattern in physics, a boundary beyond which waves cannot return. The interior of a black hole is not a place in the ordinary spatial sense. Outside the horizon, one can choose to move inward or outward, accelerate, orbit, or depart. Inside the horizon, the coordinate that once behaved like radius becomes more like time. Decreasing radius is not a direction one chooses, but a future one cannot avoid. This is why saying that the singularity lies at the center can be misleading. For an infalling observer, the singularity is not like a point sitting ahead in space that might be steered around. It is more like tomorrow. It lies in every possible future path. This is one of the most disorienting consequences of general relativity. The interior of a black hole is not simply a dark room with a dangerous center. It is a region where the structure of possible futures has been rearranged. If a person fell into a very large black hole, the outside universe would appear increasingly distorted. Light from the universe behind them would be bent and concentrated. The sky would shrink into strange patterns as photons followed curved paths. Depending on the black hole's spin and the observer's trajectory, light from the accretion disk might be seen from multiple directions, with colors shifted by gravity and motion. But the observer would not see the entire future history of the universe flash before their eyes in any simple literal way. Popular descriptions often exaggerate this. Time dilation is real, but finite infalling observers have finite proper time and finite ability to receive light before reaching the singularity. The final view would be governed by the detailed geometry of the space-time and by the physical limits of the observer. Black holes are strange enough without needing myths. The question of whether black holes destroy objects is subtler than it sounds. From the viewpoint of the object, tidal forces, radiation, heating, and eventual approach to the singularity are destructive. But from the viewpoint of quantum information, destruction is not supposed to mean erasure. A book burned in a fire is destroyed as a book, but in principle the information in its exact initial state remains encoded in the correlations among smoke, ash, photons, and air molecules. Quantum mechanics insists that such evolution is reversible in principle, even when it is impossible in practice. Black holes challenge this because classical general relativity seems to remove the information behind a horizon and eventually erase the black hole through thermal radiation. The problem is not that black holes break objects. Ordinary fire does that. The problem is whether they break the rule that information is never fundamentally lost. The enormous lifetime of black holes through Hawking evaporation gives them a place in the far future of the universe. A stellar mass black hole would take vastly longer than the current age of the universe to evaporate. A supermassive black hole would last even longer, with evaporation timescales so large that they are almost impossible to imagine. Long after ordinary stars have burned out, long after white dwarfs have cooled and galaxies have dimmed, black holes may remain as some of the last large organized structures in the cosmos. In the extremely distant future, if current physical understanding holds, even these black holes will slowly radiate away, one photon at a time, until they disappear. The universe of the far future may be not a universe of stars, but a universe of cold remnants and black holes slowly giving back their mass as faint radiation. Black holes are sometimes described as holes in space, but this can be misleading. They are not empty tunnels drilled through the universe. They are regions where mass energy has curved space-time into a causal trap. The hole is not a lack of something. It is an excess of curvature. It is not a void in the sense of nothingness. It is a place where the geometry is so extreme that the usual routes through space-time converge inward. This distinction matters because black holes are not defined by the absence of matter, but by the presence of an event horizon. A black hole can form from matter, grow by matter, merge with another black hole, and possess mass, spin, entropy, and temperature. It is one of the strangest objects in physics precisely because it is both simple and rich, empty looking from the outside, but full of consequences. The term black hole also hides the fact that these objects are not perfectly black in every practical observational sense. The event horizon emits no classical light, but the black hole's environment can radiate intensely. Accretion disks shine, jets blaze, nearby stars orbit, gas clouds heat and flare. Merging horizons shake spacetime. Even Hawking radiation, unimaginably faint for astrophysical black holes, means that quantum theory does not allow perfect blackness in the deepest sense. The name is therefore both accurate and incomplete. A black hole is black at the horizon, but a black hole system can be luminous, noisy, magnetized, and dynamically active. The darkness is real, but it is surrounded by evidence. There is a special relationship between black holes and the speed of light. In ordinary contexts, the speed of light is a speed limit through space. Near a black hole, it is also part of the definition of causal structure. If even light cannot escape, then no signal can. The event horizon is therefore not simply a gravitational boundary, but an information boundary. It divides events that can influence the distant universe from events that cannot. This is why black holes are so central to modern physics. They are not merely heavy objects. They are tests of causality. They ask what it means for something to happen if the consequences of that happening can never reach the outside world. They turn the speed of light from a number into a boundary of reality. The mathematical simplicity of black holes makes them unusually powerful for theory. A star requires equations of plasma physics, nuclear reactions, radiation transport, convection, magnetic fields, rotation, and chemical composition. A planet requires geology, chemistry, atmosphere, impact history, and internal structure. A classical black hole, once settled, requires only mass and spin in realistic astrophysical cases. This simplicity allows precise predictions. It also creates the information problem. If black holes have no hair, where did all the details go? The same feature that makes them elegant makes them disturbing. They are simple because general relativity strips away almost everything. Quantum mechanics then asks whether that stripping is only apparent or truly fundamental. The process of black hole merger can be divided into inspiral, merger, and ring down. During inspiral, the two black holes are separated enough that their motion can be modeled as orbiting compact objects losing energy to gravitational waves. During merger, the horizons distort, approach, and become a single common horizon in a fully nonlinear regime of general relativity that requires numerical simulation. During ring down, the final black hole settles into a Kerr state by radiating away distortions as gravitational waves. Each stage tests a different aspect of gravity. Inspiral tests relativistic orbital dynamics. Merger tests strong field nonlinear gravity. Ring-down tests the no-hair theorem. A single gravitational wave event is therefore not one measurement, but a sequence of tests compressed into a fraction of a second. Numerical relativity was essential for interpreting black hole mergers. For decades, solving Einstein's equations for two black holes spiraling together was one of the hardest problems in computational physics. The equations are nonlinear. Coordinate choices can produce instabilities, and the horizons and singularities must be handled carefully. Major breakthroughs in the mid-2000s finally made stable simulations of binary black hole mergers possible. Without those simulations, LIGO's detections would have been much harder to identify and interpret. The templates used to match gravitational wave signals rely on enormous banks of theoretical waveforms. When a signal passes through Earth, it is recognized because human mathematics has already taught computers what space-time should sound like when black holes collide. There are black holes in binary systems that emit X-rays because they are feeding from companion stars. These systems can alternate between states, quiet periods, bright outbursts, hard X-ray states dominated by hot inner flows. and soft states dominated by thermal disk emission. Astronomers study these state transitions to understand how accretion changes near compact objects. Some stellar mass black holes launch jets in certain states, creating microquasars, small-scale analogs of the much larger jets launched by supermassive black holes. Because stellar mass systems evolve on humanly observable timescales, they can serve as laboratories for processes that take far longer around supermassive black holes. The physics scales with mass. A supermassive black hole may take years to do what a stellar mass black hole does in seconds or days. The masses of black holes carry the history of the stars that formed them. Stars with low metallicity, meaning fewer elements heavier than helium, lose less mass through stellar winds during their lives, and can therefore collapse into heavier black holes. This is one reason gravitational wave events involving relatively massive stellar black holes are often interpreted as evidence for formation in low metallicity environments. Metal-rich stars, by contrast, can shed more mass before collapse, leaving smaller remnants. The black holes we detect are therefore not only objects in the present, they are fossils of stellar chemistry. Their masses remember the composition of the gas clouds from which their parent stars were born. The boundary between neutron stars and black holes is one of the most important open questions in compact object astrophysics. Observations have found neutron stars above 2 solar masses, proving that dense matter can support at least that much mass. The exact maximum mass depends on the equation of state of ultra-dense nuclear matter, which is not fully known. Above that maximum, collapse to a black hole should occur. Gravitational wave events involving objects in the range between the heaviest known neutron stars and the lightest confidently known black holes are therefore especially interesting. They may reveal whether a mass gap exists, whether it is partly observational, and how nature makes compact remnants. In this boundary region, nuclear physics and gravitational astronomy meet. A black hole spin can tell a story about its growth. If a supermassive black hole grows mainly by prolonged accretion from a disk with a stable orientation, it can spin up rapidly. If it grows through many randomly oriented small accretion episodes or chaotic mergers, its spin may remain moderate. If it merges with other black holes, the final spin reflects the masses and spin orientations of the progenitors. Measuring spin across populations could therefore reveal whether black holes grew smoothly, violently, or in alternating phases. Spin is like a memory, but a compressed one. It does not preserve every detail, but it carries a statistical imprint of past feeding and merging. Black holes can also be used to test whether general relativity remains correct in the strongest gravitational fields accessible to observation. General relativity has passed every experimental test so far, from the precession of Mercury's orbit to gravitational time dilation, gravitational waves, binary pulsars, and black hole imaging. But most tests occur in weak or moderately strong fields compared with the regions near horizons. Black holes offer access to strong field gravity. Deviations from the Kerr metric, unexpected ring-down frequencies, shadow shapes inconsistent with predicted geometry, or anomalies in stellar orbits near Sagittarius A star could all indicate new physics. So far, the evidence remains consistent with general relativity. But the search is important because black holes are where the theory is most vulnerable and most powerful. The stars orbiting Sagittarius A star provide one of the cleanest tests of gravity near a supermassive black hole. The star S2, also called S02 in some catalogs, passed close to Sagittarius A star in 2018, allowing astronomers to detect the gravitational redshift predicted by general relativity as the star moved through the black hole's potential well. Its orbit also exhibits relativistic precession, a slow rotation of the orbital ellipse analogous to Mercury's perihelion precession around the Sun, but far stronger. These measurements do not probe the event horizon directly, but they probe the environment around a 4 million solar mass compact object with remarkable precision. They are a reminder that not all black hole evidence comes from images or gravitational waves. Sometimes it comes from watching a star trace an invisible mass, year after year, until the orbit itself becomes a diagram of gravity. The gas cloud known as G2, discovered on a highly elongated orbit near Sagittarius A star, became a test of expectations about how the Milky Way's central black hole feeds. Some astronomers initially predicted that as G2 passed close to the black hole, it might be stretched, disrupted, and partially accreted, producing a noticeable flare. The passage was less dramatic than some expected, suggesting that G2 may not have been a simple gas cloud, but perhaps a dusty object surrounding a star or a compact stellar remnant. The episode was scientifically useful precisely because the prediction did not produce a spectacular flare. It reminded astronomers that the galactic center is complex and that feeding a black hole is not simply a matter of bringing gas nearby. Angular momentum, magnetic fields, density, and the nature of the object all matter. Black holes can recoil after mergers. If gravitational waves are emitted asymmetrically during a merger, they carry away linear momentum, and the final black hole receives a kick in the opposite direction. In some simulations, especially for certain spin configurations, these recoil velocities can be thousands of kilometers per second, large enough to eject a black hole from a small galaxy or displace it from the center of a larger one. Observational candidates for recoiling supermassive black holes have been proposed, though confirmation is difficult. The idea is important because it adds motion and consequence to black hole mergers. A merger does not simply make a larger black hole quietly at the center. It can shake the remnant, move it, and change the future growth of both black hole and galaxy. Black hole mergers in galaxies are linked to galaxy mergers. When two galaxies collide and merge, their central supermassive black holes sink toward the new center through dynamical friction, losing energy to surrounding stars and gas. Eventually, they may form a bound binary. But getting from a parsec-scale binary to a gravitational wave-driven merger requires further angular momentum loss, a problem historically called the final parsec problem. Interactions with stars, gas disks, triaxial galaxy potentials, and additional black holes may help solve it. The evidence from pulsar timing arrays for a gravitational wave background is important partly because it suggests that many supermassive black hole binaries do in fact reach small enough separations to radiate strongly. The universe seems to find ways to bring its largest black holes together. Pulsar timing arrays detect gravitational waves in a completely different frequency range from LIGO. Millisecond pulsars rotate with extraordinary regularity, sending radio pulses that can be timed with exquisite precision. A passing gravitational wave slightly changes the spacetime between Earth and the pulsars, producing correlated timing deviations across many pulsars on the sky. The expected signature of a gravitational wave background is not a single chirp, but a pattern of correlations known as the Hellingsdowns curve. This turns the Milky Way into a galaxy-sized gravitational wave detector. The likely sources are supermassive black hole binaries slowly orbiting across the universe, producing nanohertz gravitational waves with periods of years. It is a quieter kind of astronomy, not a sudden collision, but a background murmur from the population of giant binaries. Space-based gravitational wave detectors will open still another part of the black hole spectrum. A detector like LISA will use 3 spacecraft separated by millions of kilometers, following Earth around the Sun and measuring changes in distance with laser interferometry. It will be sensitive to lower frequency gravitational waves than ground-based detectors, including mergers of massive black holes, extreme mass ratio in spirals, and compact binaries in our galaxy. Extreme mass ratio and spirals are especially valuable. A stellar mass black hole or neutron star slowly spiraling into a supermassive black hole, completing thousands of orbits and mapping the spacetime geometry in exquisite detail before plunging. Such signals could become some of the most precise tests of the Kerr metric ever performed. If LIGO hears black holes collide like brief chirps, Lisa may hear them as long, intricate songs. Extreme mass ratio and spirals are almost like natural probes lowered into curved spacetime. A small compact object orbiting a massive black hole gradually loses energy to gravitational waves, and because the mass ratio is so extreme, the small object completes many orbits before merger. Each orbit samples the geometry near the massive black hole. The emitted gravitational waves carry a detailed record of that geometry, including the massive black hole's mass and spin, and potentially any deviations from the Kerr solution. These signals are faint and complex, but they are scientifically rich. They turn the strong gravity region into an instrument. Instead of sending a spacecraft near a black hole, nature sends compact remnants, and future detectors may read the spacetime map from their waves. Black holes are also connected to high-energy cosmic particles. Jets from active galactic nuclei are candidate sites for accelerating cosmic rays to extreme energies. In these environments, magnetic fields and relativistic shocks can accelerate charged particles to energies far beyond anything human-made accelerators can reach. Some high-energy neutrinos detected on Earth have been associated with active galaxies, though the exact source populations remain under investigation. If black hole-powered jets produce even a fraction of the highest energy cosmic rays, then black holes are not merely endpoints of stellar collapse or engines of radiation. They are also accelerators, shaping the energetic particle environment of the universe. The particles that strike Earth's atmosphere may have begun their journey near a supermassive black hole millions or billions of years ago. The magnetosphere around a black hole is a peculiar idea because the black hole itself may not have a material surface, yet the plasma around it can organize magnetic fields into structures resembling those around rotating compact objects. In a spinning black hole threaded by magnetic field lines anchored in the surrounding disk, the rotation of spacetime can twist the fields, drive currents, and launch pointing flux-dominated jets. This is the essence of the Blandford-Znajek mechanism. The energy ultimately comes from the black hole's rotation, but it is extracted through electromagnetic fields and plasma outside the horizon. In this sense, a black hole can behave like part of an electrical circuit whose wires are magnetic field lines, and whose load is the distant jet. The machinery is invisible in ordinary light, but luminous in radio, X-ray, and gamma-ray observations. The cosmic environment around a black hole matters enormously. A black hole in empty space is almost perfectly dark, detectable only by its gravitational effects or by lensing background light. A black hole in a dense gas cloud can be brilliant. A black hole in a binary system can pull material from a companion star. A black hole in a galactic nucleus can power jets, heat gas, and regulate star formation. The same object, described by the same few parameters, can appear silent or spectacular depending on what surrounds it. This is why black holes are both simple and context-dependent. The horizon may be mathematically clean, but astronomy happens outside it, in the messy environment of plasma, dust, stars, magnetic fields, and motion. Black holes can lens stars behind them, and a lone black hole drifting through the galaxy might reveal itself by the temporary magnification and slight astrometric shift of a background star. Detecting isolated stellar mass black holes this way is difficult, but it is one of the few methods available for finding black holes that are not accreting and not merging. Most stellar mass black holes may be quiet and isolated, invisible in X-rays and silent in gravitational waves most of the time. The Milky Way may contain millions or tens of millions of them, remnants of massive stars that died over the galaxy's history. We know only a tiny fraction of this population directly. The galaxy may be threaded with dark stellar corpses, moving quietly among the stars. The number of black holes in the observable universe is not known precisely, but it is enormous. Every large galaxy likely contains a central supermassive black hole. Stellar evolution over cosmic history should have produced vast numbers of stellar mass black holes. Some estimates suggest there may be tens of millions of stellar mass black holes in the Milky Way alone, most invisible because they are not currently feeding from companion stars. Across the observable universe, the number could be unimaginably large. Yet black holes occupy a tiny fraction of cosmic volume. They are numerous, but small. Their influence is powerful not because they fill space, but because they concentrate mass and curvature so intensely. The apparent darkness of black holes also makes them useful reminders of a deeper astronomical truth. Most of the universe is known indirectly. We infer dark matter from gravity. We infer exoplanets from transits and stellar wobbles. We infer neutron stars from pulses, X-rays, and gravitational waves. Black holes are the most extreme version of this indirect knowing. They cannot be seen in the ordinary sense, but their existence is written in the motions of stars, the shapes of accretion disks, the timing of pulsars, the distortions of light, the chirps of gravitational waves, and the shadows measured by global radio arrays. Modern astronomy is not merely the science of looking. It is the science of understanding effects. The black holes at the centers of galaxies may have influenced the cosmic history of star formation. Observations show that the universe's star formation rate rose to a peak several billion years after the Big Bang and then declined. Many processes contributed to that decline: gas consumption, heating, galaxy environment, and feedback from stars and black holes. Active galactic nuclei can drive winds that remove cold gas from galaxies or heat gas so it cannot collapse efficiently into new stars. In some cases, black hole feedback may quench star formation, turning a galaxy from blue and actively star-forming to red and relatively quiet. In other cases, jets and outflows may compress gas and trigger star formation locally. The influence is not one-directional, but it is profound. Black holes help decide when galaxies keep making stars and when they grow old. The early universe poses a special puzzle because luminous quasars are observed at very high redshift, powered by black holes that already had masses of hundreds of millions or billions of solar masses. This means that black hole seeds formed early and grew fast. The first stars, known as population 3 stars, may have been much more massive than typical stars today because they formed from pristine hydrogen and helium gas with no heavy elements to cool it efficiently. Their remnants could have provided early black hole seeds. Alternatively, direct collapse black holes may have formed when large gas clouds collapsed almost directly into black holes without fragmenting into ordinary stars. Both possibilities are studied intensely. The question is not only how black holes formed, but how structure formed. The first massive black holes may have shaped the first galaxies, and the first galaxies may have fed the first massive black holes. A black hole's effect on nearby clocks is not only theoretical. Time dilation is measured routinely in weaker gravitational fields, including the corrections required for GPS satellites, whose clocks run at slightly different rates because of both gravity and motion. Near a black hole, the effect becomes extreme, but it is the same principle. Time is not universal. It is local, shaped by motion and gravity. Black holes dramatize this truth. They show that time can become so tilted by gravity that the future direction for anything inside the horizon points inward. The familiar division between space and time becomes less intuitive. What we call falling is, inside the horizon, partly the structure of time itself. The surface gravity of a black hole is related to how much acceleration would be required to hover just outside the horizon, as measured from far away. For a smaller black hole, the surface gravity is higher. For a larger black hole, lower. This is why the Hawking temperature is inversely proportional to mass. Small black holes are hotter. Large black holes are colder. An astrophysical black hole is colder than the cosmic microwave background, meaning it absorbs more radiation from the universe than it emits through Hawking radiation today. Only in the far future, after the universe cools enormously, will large black holes begin to lose more energy than they gain from surrounding radiation. Their evaporation is not a present-day astrophysical process, but a far future thermodynamic fate. The idea of a black hole remnant is one possible answer to the final evaporation problem. Perhaps Hawking evaporation stops at the Planck scale, leaving a tiny stable object containing the information that fell in. This would avoid complete information loss, but it raises problems of its own. If remnants can store arbitrarily large amounts of information, they may require an enormous number of internal states, which could lead to theoretical difficulties in quantum field theory. Complete evaporation with information encoded in radiation is another possibility. A bounce into a new region of space-time is another, more speculative possibility. No current answer is universally accepted. The end of black hole evaporation sits behind both practical and theoretical horizons, too distant to observe and too quantum gravitational to calculate with established theory. White holes are mathematical time reverses of black holes. A black hole allows things to enter but not leave. A white hole would allow things to leave but not enter. White holes appear in certain exact solutions of general relativity, but there is no observational evidence that they exist in nature, and they are generally considered physically unstable. They are useful conceptually because they show that Einstein's equations permit time-reverse structures, but the universe's thermodynamic arrow of time and the instability of such solutions make them unlikely astrophysical objects. Wormholes, white holes, and extended black hole diagrams are therefore fascinating mathematical landscapes, but one must distinguish them from the black holes astronomy actually observes. The real universe gives us accretion disks, jets, shadows, and gravitational waves, not confirmed portals to other regions. The apparent connection between wormholes and quantum entanglement remains one of the most intriguing and speculative ideas in modern theory. The ER equals EP conjecture proposes that entangled particles may be connected by non-traversable wormholes in a deep mathematical sense. This does not mean that ordinary entangled particles can be used for travel or faster than light communication. Quantum entanglement does not allow messages to be sent instantaneously. The conjecture is more subtle. It suggests that geometry and entanglement may be two descriptions of the same underlying structure. If spacetime itself emerges from patterns of quantum entanglement, then black holes are not merely objects within spacetime. They are clues to how spacetime is built. Black holes have also changed the language of information in physics. In the 19th century, entropy was a thermodynamic concept connected to heat engines and disorder. In the 20th century, it became connected to information through statistical mechanics and information theory. Black holes force these meanings together. Their entropy is not just a measure of ignorance about hidden microscopic states. It is tied to horizon area, gravity, quantum fields, and the maximum information that can fit in a region. This changed how physicists think about space itself. A region's information capacity may scale not with volume, but with boundary area. The lesson from black holes may be that the universe is less like a container filled with information and more like a system whose boundaries and information are inseparable. The phrase maximum information density may sound abstract, but it has physical consequences. Try to store too much information, too much energy, in a small enough region, and the region becomes a black hole. In that sense, black holes represent the ultimate limit of storage. They are not only gravitational endpoints, but informational endpoints. The Bekenstein bound, related to this idea, suggests a maximum entropy for a finite region of space with finite energy. This is one of the reasons black holes connect gravity, thermodynamics, and computation. They are the places where asking how much can be known, how much can be stored, and how much can be hidden becomes the same as asking how spacetime behaves. The black hole information paradox is often described as a crisis, but it has also been extraordinarily productive. Many of the most important ideas in quantum gravity emerged because the paradox refused to go away. Holography, black hole complementarity, the firewall debate, islands, replica wormholes, soft hair, and new approaches to quantum error correction in spacetime all trace part of their lineage to the question of what happens to information at a horizon. A good paradox in science is not merely a problem. It is a machine for generating better questions. Black holes have been such a machine for half a century. They keep revealing that our separate theories of gravity, quantum mechanics, and information are not truly separate. Some black holes may be born without bright supernova explosions. In direct collapse, a massive star's core can fall inward so completely that little energy is deposited in the outer layers, and the star may simply vanish or produce only a faint transient. Astronomers have searched for disappearing massive stars as possible evidence for this process. Such events matter because they affect the population of black holes and the chemical enrichment of galaxies. A normal supernova ejects heavy elements into space. A failed supernova locks more material into the remnant and releases less light. The death of a star can therefore range from a brilliant explosion to a near-silent disappearance. The black hole is the same kind of endpoint, but the path to it can be luminous or almost invisible. Pair instability physics shapes the masses of black holes formed from very massive stars. In extremely hot stellar cores, gamma-ray photons can convert into electron-positron pairs, reducing radiation pressure and causing partial collapse. This can trigger explosive oxygen burning. Depending on the star's mass, the result may be a pulsational pair instability event that ejects mass before final collapse, or a full pair instability supernova that completely destroys the star and leaves no remnant. This creates an expected shortage of black holes in certain mass ranges, though the exact boundaries depend on stellar rotation, metallicity, and uncertain modeling. When gravitational wave detectors find black holes in or near these ranges, astronomers ask whether they formed by ordinary stellar collapse, repeated mergers, or more exotic channels. The mass of a black hole can therefore become a clue to the physics of the star that died to make it. The black holes in globular clusters may grow through repeated interactions. Globular clusters are dense, ancient star systems containing hundreds of thousands or millions of stars. In such crowded environments, black holes can sink toward the center through mass segregation, form binaries through dynamical encounters, and merge. The remnant of one merger may remain in the cluster if the recoil kick is not too large, allowing it to merge again later. This hierarchical merger process could build black holes more massive than ordinary stellar collapse would produce. It is one possible route to intermediate mass black holes. It also leaves signatures in spin. A second-generation merger remnant may have a characteristic spin inherited from the previous merger. Gravitational wave catalogs may eventually reveal how common this process is. Intermediate mass black holes are important because they could be the missing link between stellar mass and supermassive black holes. If they exist in large numbers, they might serve as seeds for supermassive black holes, growing through accretion and mergers over cosmic time. They might also reside in globular clusters, dwarf galaxies, or the stripped nuclei of galaxies that lost their outer stars through interactions. Observational evidence remains difficult because an intermediate mass black hole's sphere of influence is small, and if it is not accreting, it may be almost invisible. Some candidates are identified through unusually bright X-ray sources, peculiar stellar motions, or gravitational wave events. Each candidate must be treated carefully. The category is plausible and increasingly supported, but the population is still not mapped with the clarity astronomers have for stellar mass and supermassive black holes. A black hole sphere of influence is the region where its gravity dominates over the random motions of surrounding stars. For a supermassive black hole in a nearby galaxy, resolving this sphere of influence allows astronomers to measure the black hole's mass dynamically. For distant galaxies or smaller black holes, the sphere may be too small on the sky to resolve with current telescopes. This observational limitation shapes what we know. The black holes easiest to measure are not necessarily typical. They are nearby, massive, active, or surrounded by convenient tracers. Astronomy is always partly the study of selection effects. The universe contains all black holes, but our instruments reveal only those that leave signatures bright, loud, or clean enough to detect. The centers of galaxies can contain not only one black hole, but sometimes two, especially after galaxy mergers. Dual active galactic nuclei occur when both central black holes are feeding while still separated by hundreds or thousands of light years. Closer binary supermassive black holes are harder to confirm because their separation becomes too small to resolve directly. Astronomers look for periodic brightness variations, disturbed jet structures, offset emission lines, and other indirect signatures. Confirmed close binaries are scientifically important because they are the precursors of the low-frequency gravitational waves that pulsar timing arrays and future space detectors seek. They are also messy. Gas, stars, and dust can mimic or obscure the signs. Finding them requires patience, long monitoring, and caution. The Fermi bubbles above and below the Milky Way's plane are enormous gamma-ray structures extending tens of thousands of light years from the galactic center. Their origin is still studied, but one leading possibility is that they were inflated by past activity from Sagittarius A star, perhaps a period when the black hole accreted more material and launched outflows. If so, our currently quiet central black hole has not always been quiet. It may have gone through episodes of much stronger activity in the relatively recent galactic past. This transforms the way we imagine the Milky Way. The center of our galaxy is not simply a still point around which stars orbit. It is a sleeping engine with evidence of previous awakenings written in enormous lobes of high-energy emission. The environments of black holes can produce some of the most extreme temperatures in the universe. Accretion disks around stellar mass black holes can reach millions of degrees. Coronae of hot electrons above disks can scatter lower energy photons into X-rays. Relativistic jets can produce synchrotron emission and inverse Compton radiation across enormous energy ranges. But temperature near black holes is not always intuitive. The Hawking temperature of a large black hole is extremely cold, while the gas just outside it may be extremely hot. The horizon itself is not a furnace in the classical sense. The heat we observe usually belongs to the matter struggling outside, not to the hole's surface. A black hole can be thermodynamically cold and astrophysically surrounded by fire. The role of magnetic reconnection near black holes is an active area of research. In highly magnetized plasma, magnetic field lines can break and reconnect, rapidly converting magnetic energy into particle acceleration and heat. This process may contribute to flares near Sagittarius A star and other accreting black holes. It is also important in the dynamics of jets and coronae. Magnetic reconnection occurs in the Sun's corona, in Earth's magnetosphere, and in laboratory plasmas, but near black holes it happens in curved spacetime, in plasma moving at relativistic speeds, near horizons and ergospheres. The same basic plasma process becomes part of a much more extreme environment. A small flare from the galactic center may be the visible trace of magnetic fields rearranging themselves near the edge of no return. Black holes can be quiet for long periods and then suddenly flare when the environment changes. A gas cloud, a star, an instability in an accretion disk, or magnetic turbulence can temporarily increase the amount of material reaching the inner region. The flare may last minutes in a stellar mass system, hours near Sagittarius A star, or months to years in a tidal disruption event around a supermassive black hole. Timescales scale with mass because the size of the system scales with the gravitational radius. This scaling is powerful. It allows astronomers to compare small and large black holes as versions of similar physics running at different speeds. A stellar mass black hole is like a fast clock. A supermassive black hole is like the same clock slowed down to cosmic tempo. The fact that black holes have no material surface is observationally important. A neutron star has a surface. Matter falling onto it can strike the surface, producing bursts, thermal emission, or other signatures. A black hole has no surface outside the horizon. Matter can disappear across the horizon without a final impact flash. Comparing compact objects with and without surfaces helps astronomers distinguish black holes from neutron stars. In some systems, the absence of surface emission supports the black hole interpretation. This is subtle but profound. The evidence for black holes is not only that something is massive and compact. It is also that matter behaves as if there is no hard surface where the fall ends. The event horizon theorem in classical general relativity implies that the area of black hole horizons cannot decrease, provided certain energy conditions hold. When two black holes merge, the area of the final horizon must be at least as large as the sum of the original horizon areas. Even though the final mass is less than the sum of the initial masses, because energy is radiated as gravitational waves. This was tested observationally using gravitational wave data from black hole mergers, comparing inferred horizon areas before and after merger. The results are consistent with Hawking's area theorem. It is a beautiful example of abstract geometry becoming measurable astronomy. A theorem about horizon area, proved in the language of classical relativity, leaves a signature in the waveform recorded by detectors on Earth. The relationship between black holes and entropy also suggests that black holes are the most entropic objects of a given size. If one tries to put too much entropy into a region, gravitational collapse may form a black hole, and the black hole's horizon area sets the limit. This has deep implications for cosmology because it connects the growth of structure, the arrow of time, and gravitational degrees of freedom. The early universe was hot and dense, but, in a gravitational sense, low entropy because matter was distributed smoothly. As gravity clumped matter into stars, galaxies, and black holes, gravitational entropy increased. Black holes may dominate the entropy budget of the present universe. The quiet darkness at galactic centers may contain more entropy than all the starlight surrounding them. Black hole shadows are expected to be nearly circular in general relativity for many viewing angles, even for spinning black holes, because the lensing structure is strongly constrained. Small deviations can arise from spin, inclination, plasma emission, and environmental effects. If future observations found a shadow shape strongly inconsistent with Kerr predictions after accounting for plasma uncertainties, it would be a major clue to new physics. But interpreting images is difficult because the bright ring is not a clean geometric outline drawn on the sky. It is produced by turbulent plasma, magnetic fields, relativistic motion, and light bending. The challenge is to separate the spacetime signal from the astrophysical foreground. Black hole imaging is therefore both a triumph of gravity and a problem in plasma astrophysics. The Event Horizon Telescope is sometimes described as an Earth-sized telescope, but that phrase hides the elegance of very long baseline interferometry. Telescopes across the world observe the same source at the same time, recording radio waves with precise timing from atomic clocks. Later, the data are brought together and correlated, reconstructing the interference pattern that a telescope as large as the separation between sites would have measured. Because the data volumes are enormous, hard drives have physically been shipped from remote observatories for processing. The image is not a simple photograph. It is a reconstruction from sparse measurements in Fourier space, tested by multiple independent imaging methods. That the resulting ring persists across methods is part of what makes the image scientifically convincing. The Milky Way's central black hole is harder to image than M87 star, even though it is much closer. Sagittarius A star has a much smaller mass, so the gas near it orbits and changes on timescales of minutes rather than days. During an observation, the source evolves, making the image reconstruction more difficult. It is like trying to take a long exposure photograph of something that changes while the shutter is open. M87 star, being much more massive, changes more slowly and is easier in this respect, even though it is far more distant. This is a useful reminder that astronomical difficulty is not determined by distance alone. Size, variability, brightness, scattering by interstellar material, and observational wavelength all matter. Light from Sagittarius A star is also affected by scattering as it travels through turbulent ionized gas between the galactic center and Earth. This scattering blurs radio images, especially at longer wavelengths. Observing at millimeter wavelengths reduces the effect, but does not eliminate all complications. The Event Horizon Telescope image of Sagittarius A star therefore represents not only a measurement of a black hole shadow, but also an achievement in correcting for the messy interstellar medium between us and the center of our galaxy. The path from horizon-scale plasma to a reconstructed image on Earth passes through 26,000 light-years of galaxy. The image is local and cosmic at once, a view of the center, filtered by everything in between. Black holes challenge language because many ordinary words fail near horizons. Falling, inside, outside, now, surface, center, before, after, all of these words carry intuitions shaped by weak gravity. General relativity does not remove meaning from them, but it forces them to be defined carefully. What is simultaneous for one observer is not simultaneous for another. What looks frozen from far away is crossed in finite time by the infalling object. What seems like a boundary with no substance becomes one of the most important surfaces in physics. Black holes are not only difficult because the equations are hard. They are difficult because they require ordinary intuition to be rebuilt. The philosophical appeal of black holes comes partly from their simplicity. They are places where the universe seems to say, here is the limit of observation, here is the limit of theory, here is the limit of causality, and yet here are measurable consequences. They are not mystical. They are not supernatural. They are physical objects governed, as far as we can tell, by equations. But they sit at the edge of what those equations can explain. This combination, rigorous science and genuine mystery, is rare. Many mysteries dissolve when they are studied. Black holes have done the opposite. The more precisely they are studied, the sharper and more consequential their mysteries become. For all their darkness, black holes have made the universe more knowable. They gave astronomers new tests of general relativity. They opened gravitational wave astronomy. They forced quantum gravity to confront information. They explained quasars, active galactic nuclei, X-ray binaries, and the powerful jets that sculpt galaxies and clusters. They provided images that turned mathematical horizons into observed shadows. They connected the smallest scales of Planck physics to the largest scales of cosmic evolution. A black hole is an endpoint for matter, but not for inquiry. Around the boundary where light cannot return, science has found one of its richest sources of questions. There is a particular kind of wonder appropriate to black holes that is different from the wonder appropriate to other astronomical objects. A galaxy is vast, beautiful, full of stars and light and structure. A nebula is colorful and intricate. A pulsar is precise and regular. But a black hole offers something different. It is the place where our best understanding of physical reality reaches its boundary and stops. It is where general relativity, one of the most precisely tested theories in the history of science, produces singularities that it cannot describe. It is where quantum mechanics and gravity, the two great theories of the 20th century that have never been fully reconciled, are simultaneously required and simultaneously insufficient. It is where information, the most fundamental currency of physics, appears to be destroyed, in violation of quantum mechanical principles that everything else we know confirms. It is where spacetime ends. And yet from this boundary, this edge of the known, the physics has returned some of the most beautiful and most productive mathematical insights of the past 50 years. The entropy and thermodynamics of black holes have given us the holographic principle. The information paradox has driven theoretical innovations that have transformed quantum gravity research. The gravitational wave signals of merging black holes have opened an entirely new observational window on the universe and confirmed predictions of general relativity that no other test could approach. The Event Horizon Telescope images of black hole shadows have turned abstract theoretical objects into observed astrophysical phenomena. The black hole is, paradoxically, one of the most productive objects in physics precisely because it is the one place where physics runs out. And tonight, as you let go of the day and drift toward the darkness behind closed eyes, the universe continues to contain all of this. The invisible masses at the centers of galaxies, the quiet inflation and deflation of space-time as gravitational waves pass, the incomprehensible interiors where our best mathematics stops, and the slow, patient evaporation of ancient objects into radiation that carries more information than any book ever written, in a language no one has yet fully learned to read. Sleep well. Good night.